Hello everyone and welcome to a new episode of All Things IDA. In today's episode, I'm gonna continue the PE file format series and talk about the relocation section. We're going to cover the relocation types, how to parse it in the PE/PE plus, and then also how to use IDA programmatically to retrieve this information from the database. With that, let's get started. The first thing is let's just pick some binary from disk. I'm gonna pick Explorer from my system just for the sake of illustration. I'm gonna pick Explorer 64 for example and disassemble it with IDA. Now it's important to note that we need to make sure we have manual node enabled because this will let IDA put the header into the database alongside other sections. Now if we were doing this from memory, we will have this information already in the module memory. Everything will be mapped, but since I'm not gonna be doing this in the debugger, I load this file in manual mode. This is gonna let us specify the preferred base, and then it will ask us to start loading the sections. This is the overlay. That's probably the signature part in the PE file. Load the header. This is the most important part, at least for our script, so we can also inspect the database. It also asked me to load the P data and so on, topic for the future. Alright, so what I want from this really is the header here, and eventually in the header we have another image data directory, and that directory would be the relocation table pointer. This directory index is 5 as we will see in WinNT. So we have the export directory which we spoke about at image data directory index 0, the import, we spoke about TLS, and the relocation. This is the 6th entry, and this is basically the image data directory for it, which has a virtual address inside. So if we follow this usually coincides with the relog section itself. So we will have a relog section, and it is a section. We don't necessarily have to rely on the fact that it is called relog and we have to find it in the section. It's really looked up by the image data directory. So here, this is the location, and that's what we're going to talk about, how to interpret. Same story if we're using Hiew, for example. We have the PE file F8 to go to the headers, and then for example I will press F10 for the data directories, and I have the entry here which is the fixups. Same story, this is the same address we have in IDA. And also if we check the sections as well, it happens to be the relocation. So we're on the right track here. Now we're gonna learn how the loader interprets this and fixes up the database. So the point of the relocation is when we have a binary, for example, it has a preferred loading image base. So on disk it will have, I prefer to be loaded at this image base. But if there is collision, some other module, let's say, took that address. This is more frequent in DLLs than executables. But when there is this conflict, then we have to go and fix all the locations that hard codes absolute addresses with updated information so that the code does not crash. So if it's not relative to the IP address, sometimes it's full pointer. It will be hard coded as a full address in function of the old image base addresses. And if that image gets moved around due to collision or ASLR, for example, we need to find the locations in our image, in the whole image, could be in text, could be in data, and then add a delta, the difference between the new image base and the old image base, so we update the hard-coded addresses in our image. Like this, our program continues to function. And this is part of the loading of a PE file into memory. So right now, since we're static, we have the preferred image base correctly and everything is gonna be correct. Let's go to the beginning here, and I'm gonna show you the first instance of a relocation so we can reason about it visually. So IDA comes with a plugin. Here we're gonna see it. Let's press Ctrl 3. It says jump to nextfix, and this is a plugin on the file disk. It's called nextfix, and we can just invoke it, and it takes us to the first location where we might need to do relocation. So I'm going to show the opcodes here, and this is a hard-coded address. If the image moves, then this address referring to this older image base is not going to be correct anymore. So if there's no relocation information and the image moved, this pointer will be pointing somewhere either invalid or to something else. So relocation is encoded in such a way to tell the PE loader that, hey, please update this location. If I invoke the same plugin again, this is another fixup, and there will be as many fixups as needed based on the program. For example, here's lots of pointers that needs to be relocated to the new image base by applying the relocation information. So if I simply do edit segment and rebase the whole program, and suppose now we move the base to some other address, we move the whole program. IDA will use the fixup information, to see we selected this, to update everything. So now those pointers will not remain like this. Alright, so now we understand why we need relocation. Let's go back to the relocation block here and explain the format and how we can interpret this whole section, which is 6000 hex. Alright, so going back to MSDN here in the description of the relocation section, it will say that once we follow it to the address, so once we follow it here, then what to expect. So we'll expect what we call a base relocation block, and each block starts with the following structure. It will be of size 8, and it will have the page RVA and the block size. And we'll talk about the meaning of this. But the first thing we know is we're gonna be applying a base relocation structure. So let's do that. So the base relocation block programmatically in the Windows header is of type image base relocation. So let's go and apply structure here. So Shift F1, insert, and let's import this one and find it. So this is what we want to import into our database. And now we can apply it. So here we can simply apply the image base relocation. And if we expand this, we see it has virtual address and size of block. So by definition, each block here represents the base relocation for a 4K page. So there will be multiple blocks because every block can only describe relocation information for one page of memory. So for example, if we have our text section here, every 1000 hex is a page, or 4K, and it's very big, so there are so many pages, and if we have relocation information within that range, it depends how much information, but for every page we will have a relocation block. So we should assume that here the block, this is just one block describing this RVA, and this is the size of this block. Now if there's another memory page, then there will be another block, so we can already verify that theory. So we have one block of size 3BC. So if we go here and say jump to 3BC advanced, this is the second block. So here we can just say block 2 and apply. And now this is describing this page here, which happens to be the next page. So this one is 313 and this is 314, and it has a size of 3FC. So if I also jump to the next relocation block, this is another block describing the second page. And so there will be so many blocks within the range of the image data directory entry of the relocation. So again, if we go here to the header and we'll see the relocation here, it has a size. So between the beginning of the relocation table all the way to the whole size of that directory, we can fit as many blocks within that range. So that's the first block, and then given the block size, and we know the range, so we know the relocation entry will finish after this much. So if we go here and jump to this is the end of the relocation. That's it. So we have so much relocation blocks defined within the boundaries of the image data directory. And now that we know the block header, we should be able now to describe what is inside the block. We have the size of block, but then there is 3BC bytes for the whole block. So what happens here until we reach the next block? So what happens between those sections here? So this is the second block, and what is this? So now we're gonna explain the entries in the block after we describe the header of a block. Now that we know the header, the description here next says, okay, followed by the block size. After the block size, then we have a set of entries. And the entries, each entry is just 2 bytes, one word. And it has the following. So we'll have an array of words, just 2 bytes, which encode a bunch of things. So this is 2 bytes, one word, and then split into bits. We have the 4 bits, which is the type, and it's stored in the high 4 bits of the word. So we're talking the leftmost. There will be 4 bits describing the type, and then we see what kind of types. So here we have different kind of types of relocations, and sometimes there will be additional data after the offset depending. For example, here with adjustment, to say, okay, if you find this types and the next word is a parameter to this relocation type. But we will not run into the case, at least I couldn't find input files applying this type of relocation. As we'll notice on 32-bit P files, on x86 at least, we will encounter just one kind of relocation, and on 64 we'll usually encounter just another one kind of relocation. I haven't seen, like, I don't work with MIPS, so I haven't seen this kind of relocation type and so on. There are relocation types for ARM architecture and so on. So every entry, which is, so here we have one entry, DW, and so on. Every entry here has 4 bits. The high 4 bits will be the type, and the lower 12 bits will be an offset, and that offset is simply added to the virtual address and the relocation block. So we said that the relocation block here gives us the page RVA, and then the entry itself, the offset within the page itself. And so since we have multiple blocks and every block will describe a page RVA, this is just the base of the page. Now we can say what offset within that page we need to apply a certain relocation type here. So if we want, for example, I can make an array describing how many entries I have here. So let's say here rel entries 1, it should be DW, but now we need to know how many entries. We can compute that, and the size of the block here, it will say size of the block including the RVA and the field size. So the total number of bytes in the base relocation block, the whole block including the entries, is described in the size. So this is the size, which encompasses everything including the entries. So if we really want to know how many entries alone, what we can do is gonna make an array and say, okay, how many entries? Well, this is the size, but we are here already, so we have to skip 8 bytes. This is 8 bytes, size of the actual header, and over 2. This should give us the actual number of entries based on the total size. So total size is this whole thing, but we are excluding the header by doing -8 and then simply dividing by 2 because every entry is 2 bytes. This should give us a proper array size here. This describes all the entries and exactly finishes at the second block. So this is how we know how many entries we have. Now let's interpret one entry just for the sake of information. What's the first relocation entry? So let's take entry. So let's take entry equal IDA API.get word at here. So I'm putting the cursor here and we'll break it down. So the first higher bits, we're gonna get them, which is the type, is the entry, and we're gonna shift it by 12 here. And the offset is gonna be the entry and this. This will really let us access the high 4 bits by shifting 12, the whole entry, and here the lower 12 bits by simply ending by the proper 12 bits here. And now we have the offset within the page. So let's say the page here, the base, let's just hard code it for now, 313123 here, for example. And we have here get image base function. We're gonna use that, and we're gonna say relocation entry 1, for example, applies at this address here, and it has this type. And let's see what's the result here. So we are in the right address here, and let's check it out. So we have relocation entry 1 at this address, because I did add the image base to get the full VA. So this is the full VA, type 10. So this is one relocation entry, and this is what I started my example with. This is one relocatable entry, and we should apply the relocation of type 10. So now let's explain quickly the types of relocations. So we know where to apply, what kind of type, but we don't know exactly how to apply. We know where, we know all the information. So how to apply the relocation, how to patch that memory location that we know is in need of relocation. So this is where the relocation types come into play. And what we saw here is number 10, which is image relocation based directory 64. What does it mean? It means we go to the target, we go to our destination. So this is where we need to apply. This is a DQ, which is 64, and that's basically here. We need to apply the delta, the difference between the old image base and the new image base. That delta, we simply have to apply it, the difference, on the 64-bit field. So all we have to do is simply read that address here as a 64-bit value and add to it the delta. That's it. This is the type 10. For example, if we were working with a PE, not PE plus, 32-bit, we will encounter the type 3, which simply says go to the target we need to apply a relocation and then simply add 32-bit. So it's gonna be the same. We will see a DD instead, and we will add to that pointer, 32-bit pointer, the difference. There are other types. For example, here it says based high. It says the base relocation adds the high 16-bit of the difference. So we take the delta and take the high bits of the delta and add them to the 16-bit. So we dereference the destination we want. We take 16 bits and then we add to it only the high part, only the high 16 bits of the delta. So we have the delta, we take only 16 bits and we apply it. We have another type, based low. Here as well it says add the low 16-bit of the difference. So we take the delta, we take only 16 bits of it, and then we go to the destination, interpret it as 16-bit field, and then simply add to it the delta, which is truncated to 16 bits. And there will be different kind of relocations and how you should be interpreting them. Let me show you a code snippet just to simulate applying relocations. So going here to this snippet, assume that we have calculated the delta, which is the preferred, the new base minus the old base, and then we want to apply the relocations. So we have the start of the relocation block, we have the entries, which is after the block, and now we go for every entry. For example, we get the entry, we deduce the type, then the offset. The address to patch is the image base plus the page RVA plus the offset and the page. This is the final destination. We switch on the types. So if it's image rel base absolute, based on documentation, this is of type 0, we should skip it, and this is just for padding. And there's a requirement to say that each block should be starting at 32-bit boundary. So there will be a type that's just used for padding. So we skip entry 0 and let's focus on, for example, high-low type 3. This is for 32-bit PE files, the most common relocation type. We take the destination we want to adjust and we simply add to it the delta. We interpret it as 32 bits. 64 bits here, type 10. We take the destination address as a 64-bit value and we add to it the delta. And different relocation types based on the description, we just simply have to interpret it accordingly. So going to the database, the first relocation, the final address here we computed from this formula is this. Relocation type is 10. If we want to fix this up, we are looking at this case here, which we read the value as 64-bit and add the delta. So we read this value, which will be, this is the dereference of this. This is the address and this is the value. So here we can show it to you as hex. This is the value, we read it, we add to it the delta, we patch it back to the address we need to relocate. And that's how we do relocations. So now let's look at the code. So I wrote a script and we're gonna do the same stuff like from previous videos. We're gonna get the base, then get the anti-headers, then we get directory 5, which is the relocation. We get the virtual address and the size of the whole relocation directory. We have the start of the relocation directory and the end. This will dictate how many blocks, and then simply retrieve the block. So image base relocation, this is basically here just a typed object from app call, so we can parse the image-based relocation type. The number of entries is simply the size of the block minus 8 divided by 2, we get the number of entries. For every entry in that specific block, we get the value, and then we take the type, take the offset, and we print it. So here all I'm doing is just dumping that information. Then we advance to the next block as long as we are still within the directory. So let's check it out. Now if we run this, we should be able to see everything dumped in order, and relocations are sorted by the virtual addresses. So here let's run the script. Now it will parse everything, and here it says okay, our first relocation block, which is here the first relocation block, it has this much entries. This is the row size, but then when we compute the entries we have this much entries. It's describing the page at this RVA, so if we add to the image base we should get the full destination. So this is here, and then now it iterates for every entry. So for every single word now it decodes it. It says okay, first entry at 8, this is the type 10, this is the offset, well we can see it here already, and it's gonna apply the fixup at this Y image base plus relocation block .rva plus offset, and we have it. So we can just randomly sample a bit. For example, let's see this fix up here, which is of type 64. So these are valid. We can see these are hard-coded 64-bit pointers. Makes sense. Just randomly scrolling. Let's see here. Another pointer, another table apparently we need to fix up as well. Pointers. Now the thing is, in 64-bit, most calls, so we don't see much in the text section because they're all IP relative. So that's why they're fine. So we have relative calls, the E8 opcode, that's fine, no need to relocate since it's not hard coding anything, is relative. So when the image shifts, everything shifts. Just randomly sampling, for example, same story, and it will be the same story mainly. These are all entries that are related to pointers that needs to be relocated and so on. So this is the code. Now if I apply the same in 32 bits, so here I have the same story but 32 bits, and run the script. So let's just run the script, and we should see as well the type 3, which is 32-bit fixups, and let's just sample it. So for example, okay, here this is a DS. This is a good example. Let's show you the opcodes. Here we have FF15. This is the call dword pointer. This is the hard-coded address 72A260, and definitely if we move the image, this pointer here, this we'll have to patch this entry here, so at FA and B and C, so from C. So here this is 490FC. We're gonna patch this by adding to this value the delta as a 32-bit number. Let's see another one. Same story. Any call memory location, not relative call, then we need to adjust. Any relative call on the other hand, like this is E8, this is based on the IP. So we simply take the address, dereference this, plus 5 will take us to the destination. So if we do 01F, DC, D0 plus 5, that's the address we need to go to. So if I want to simulate from here to go to that destination, let's call it F1. We just simply go plus this, and we are in F1. And so these don't need relocation, but any data call will need relocation. So this is it for manually parsing the PE files. So I'm gonna quickly cover the IDA Python and the SDK and the way IDA stores this relocation information. Okay, as usual, gonna go to the SDK, and everything related to the relocations in IDA is in the fixup.hpp file. And we can think of IDA as a way that abstracts fixup information or relocation information disregarding the input file. So IDA tries to be generic and free of operating system specificities. So for example, it has its own relocation types, fixup offset 8, offset 32, like this is what we have, type 3 in Windows headers, and we have here type 10 in as well Windows header. Then as well, to be generic for IDA to capture a fixup, it has a fixup data structure where it has the fixup type, some flags, base, and offset. And this data is enough to convert operating system related relocation information into an IDA relocation information. So we can have a fixup data that can give us the information we need as if we are parsing it in raw format. So for example, we have a function here called getFixup. We give it an address and it will fill up the fixup data. So for example, if we go back to the first entry here, if we get the fixup information about this one, we will get that it should be of type high64 here, offset 64, and we should have this information captured. So with respect to fixups, they are populated by the file loader. We haven't spoken about file loaders yet, but the file loader's responsibility as well, if it wants to encode fixup information into the database. And here this is from the SDK amiga.cpp, it's a file loader, and part of the loading aspect, not just putting the bytes into the database, as well it is adding fixup data. It's interpreting that file's format relocation and translating them to IDA type of fixups, and then simply saving the fixup data so that later we can enumerate the fixups in IDA. So we can say, for example, get first fixup EA, we get the first relocatable entry, and next, once we have the addresses, we can then get fixup information for the address. So I'll show you that here. If we replicate the same output, so here the first one was here, for example, and so on. Now, if we run the snippet here I prepared, it's gonna get the first fixup and then call get fixup, populate for me a fixup data entry at a given address, which is we are enumerating all the fixup locations, and let's simply display the types. We should now, when we run it, we should get the first location here. Let's run it. Okay, and here, let's see, this is exactly this, and fixup 12, and we said 12 is the fixup data offset 64 here, 12. And so that's how IDA does it. So when we in IDA load a file, we can delete the input binary file. We can delete it completely. So if we then say edit segment rebase, and we said in the beginning, we say apply fixup, what it's doing is going back and enumerating the fixup that the loader stored in the database and applying the fixups. And we can as well see it in this sample here. There's the move, there's a callback as well where we can relocate the database. And if we want to relocate a PE file, the PE file loader behind the scenes is doing something similar. It's going to enumerate all the things stored at the loading phase, and based on the fixup, simply patch the database to update the pointers or whatever needs to be relocated. Alright, so that's it for today. We covered in depth the relocation information, how to parse them by hand, how to write a script, how to count the entries, how to interpret the relocation types. And then also we spoke about how IDA does relocation handlings in a universal manner, disregarding the input file. And this is mainly the responsibility of the file loader. And hopefully we'll talk about file loaders in the future. Thank you, and I'll see you next time.